Potential energy diagrams follow the chemical energy stored in the compounds that are reacting as a reaction progresses, and they are a big deal in the world of chemistry. So on the y-axis, PE stands for potential energy, and keep in mind that chemicals want to have a lower energy. So the universe wants to go to lower energy positions. So it's quite likely that a reaction will be exothermic, and the energy level will end up lower at the end than at the beginning, with less energy stored in the chemicals. But let's look at this, what's on the x-axis here. You hardcore scientists out there are maybe asking, like, well, what does that mean? What are we actually measuring when we say a reaction progress? And the answer is, it depends on the specific reaction. So you might have a reaction where an atom breaks off from a compound, and in that case, the reaction progress might just be a measure of the length of the bond, and as we go to the right and the reaction progresses, the bond length gets longer, so it might measure bond length. Some reactions might involve rotation of a bond, so in other reactions this might measure a bond angle or a dihedral angle. Okay, so back to our exothermic reaction, the potential energy is going to go down, right? But not at first. First it's going to go up. In any reaction, that's the first thing that happens. The energy stored in the compound rises until it hits the top of the mountain, and then it goes down, and if it's an exothermic process, it ends up a bit lower. At a point where this point represents the products of the reaction. And the energy has to go up at first. That's why paper and wood and acetylene and everything that burns doesn't just instantly burn. You have to add energy and get it hot first. So we have to thank this activation energy for the fact that newspaper doesn't just spontaneously combust when you're holding it in your hand, because that wouldn't be fun. Well, it might be for a minute. So if the chemicals in question get this amount of activation energy, there's nothing stopping them from going over this hill and ending up at as products and having the reaction go forward. And it is this activation energy that is the most important factor in determining the rate of a reaction. This activation energy is the exponent in the Arrhenius equation. And we can more technically define it as the energy difference between the level that the reactants are at and the level of the transition state, which is right at the top of our mountain. Let's talk about the fact that this is an exothermic reaction. The only thing we need to look at to figure that out is whether the products are lower or higher than the reactants. The mountain to get there doesn't matter. This is exothermic, but if the products were up here, then they'd be higher than reactants and it would be endothermic. Another thing we know about this reaction from looking at the potential energy diagram is that it's concerted, which means it's an elementary reaction, which means that it happens in just one step. And if this is true, the stoichiometric coefficient in front of our reactant is the order of that reactant. But let's look at a more complicated case where you have a multi-step reaction. In this case, there are intermediates, compounds that are formed and then go away, and that don't appear in the overall reaction as written. How do we identify an intermediate? Well, that is any valley. So we always go up from reactants and energy. We reach a transition state at the top of the mountain, and the energy falls back down. But if it goes back up before we get to our products, the most stable form here is the intermediate. And then we'll, eventually fall back down and go to either another intermediate or products. So this would be a multi-step reaction where we'd have A going to B, which is the intermediate, and that wouldn't actually appear in the balanced equation, which then goes to, say, C, the product. Whereas the first mechanism we looked at just a second ago, with just a transition state and no intermediate, it would just be A to C directly, one step. We can see that this is an exothermic reaction, but let's ask ourselves, how exothermic is it? What if we were asked, what is the enthalpy change of this reaction? And then, again, we only care about where the reactants are and where the products are. All this, the paths you get there, doesn't matter. We don't care what path gets traveled. So we look at, the reactants energy, the product's energy, and this amount here, whatever difference between the reactants and products, that's our delta H. And you can see that we're definitely losing energy from the chemicals, so it would be a negative value. But if the products are higher in energy than the reactants, the enthalpy change is positive since the energy increases, and it's the actual value of delta H is still this difference between the product energy and the reactant energy. And still, the path doesn't matter if we're just asking about what is the enthalpy change of the reaction.